So we finished yesterday by talking about the electric potential, and there was just a graphical representation of it that I didn't get time to do properly yesterday that I'm just going to do today. So a link to this app that I'm sharing with you now is available on Google Classroom, and you can have a go with that yourself later. I suggest that you do, and you have a play with the different values in these boxes here. But this is just on screen with you now, a graphical representation of the electric potential. So this is kind of like your XY space on the pink plane that's in front of you. And then coming up vertically is the axis in this vertical direction that would be the electric potential. So the reason that I like this simulation is because it gives you a really good analogy between the electric potential and the gravitational potential. So, and you're much more familiar with the gravitational potential and you're much more comfortable with it. So imagine that we are a very, very, very long way from a mountain. And then we start walking in towards the mountain and we kind of get to the foothills and the ground starts to get ever so slightly steeper. And all of the time that we start walking up the side of the mountain, and the mountain is getting steeper and steeper and steeper all the time, but all the time that we're walking up the mountain, we are gaining gravitational potential energy, and we're having to do work to with our muscles to lift our bodies up as we climb up the mountain. Now this is a crazy symmetrical mountain, but you can see in cross section here, here's the 1/r relationship that we got from the formula yesterday. And then these green bands across are equal steps in potential energy. So this might be 10, 20, 30, 40, 50 as we go up. So you can see that looking vertically, we can see that the vertical spacing is nice and even. But then when we map that vertical spacing into the space direction, you can see that we travel quite a long way to get from, say, 10 volts to 20 volts, because it's increasing very gradually. But then we go a much shorter distance to go from 20 to 30, and then from 30 to 40, and 40 to 50. It's a lot easier if I get rid of the pink, maybe. So these are concentric circles around a point charge, but these are concentric circles that are getting closer and closer and closer together, because each line represents a uniform step up in charge. So the little pink thing is our test charge, and it's showing the force on it. So out here, far, far away from the charge, there's practically no force, but you can see that there is some voltage associated with it. And that number is going to tick up as we get closer. And this is kind of like gaining in height. Our energy is going up and up and up as we gain in height in the thing. Eventually, the arrow appears in the simulation, and that's starting to show the size of the force. It's finally big enough to show up. So more and more and more force all the time. And we're having to work harder and harder and harder against the increasing force, which means there's more energy being put in. So more and more energy as the force gets bigger and bigger and bigger. And as we cross towards the middle, this energy number is going up more and more and more as the force goes up more and more and more. So concentric circles. These are often called lines of equipotential because they are places in the two-dimensional plane where the electric potential doesn't change. So you can see that because the law is an inverse square law, which means that it's going to be symmetrical at all places around the... Stop moving. It's going to be symmetrical all the way around, which means that if I approach from any direction, it's only my distance from the center that's important in terms of... No, I've definitely broken that. It won't let me have the little charge back. In terms of approaching, so if I go for a walk along one of these green lines, it's kind of like going for a walk along a contour on a map. I'm neither gaining height nor losing height, so I'm neither gaining gravitational potential energy or losing gravitational potential energy. Likewise, if I go and take my charged particle around this green line, it will neither gain electric potential nor lose electric potential, and therefore these lines are like contours for the electric potential. They map out the space where the energy is the same. So that's why they call equipotentials, kind of equal potential everywhere along this line. Think of them as like contours on a map. Okay, so we can use this representation to look at multiple charges. So if I stick another charge in just next to it, so there's two charges now, side by side. And I could try to approach either of them. If we look at the side, over here we've got on the right and the left, we've kind of got zero or tending towards zero electric potential. It's not zero between them. It's definitely at a minimum between the two charges, but that point in the center of the screen is not the same as it is over towards the left and the right. So we do get a minimum here, but not a zero. If we take a look at it from above, again, we've got the lines closest together representing where the force is biggest, but only indirectly. We infer that by the fact that we move a small distance and the energy goes up by a very large amount, which means there must be a very large force there, because it's force times distance is the work done. When there are two charges near to each other, it does affect the potentials, as we just saw in the 3D view. It does kind of, if these were mountains, the foothills of the two come together. And then if we look off to the side, you can see that the ground is still sloping to the side of these things, just like it always was, or in this case, that the plot is still sloping. We can make one of the charges negative. Just put a minus sign in front of it. And so in our analogy, if positive charges are represented by mountains, then negative charges are these kind of infinite holes that disappear down into the ground. And that's because a positive charge represents positive potentials. We have to do work done. We have to do work to drag a positive charge in and push it up the face of one of these mountains. But a negative charge attracts a positive test charge in, so we wouldn't have to do any work at all. In fact, as the positive test charge came closer and closer and closer, in our analogy, it would be running downhill. And so it would be getting faster and faster and faster as it gained energy by converting gravitational potential energy into kinetic energy. And the same would occur here in the electric sense. It would be converting gravitational potential energy into kinetic energy, which means it's losing electric potential energy all the time and becoming more and more and more negative, because again, at infinity, we take this horizontal line in the middle here to be zero. And so if it's coming in from infinity towards a negative charge, it's going to be losing energy and ending up with less than it began with. Less than zero is negative. So that's kind of the simulation. The bit that's actually kind of examinable is just these very, very simple two-dimensional plots. And the bits to take away from this is that if the let me just turn it into a point charge on its own. If it's just a single point charge all on its own, then we're going to have a nice symmetrical plot with concentric circles based around the charge, and that we plot lines that are equally stepped in potential difference. So as I said, this might be, I mean, I know it's not, you can see, but just for simplicity, this might be 10 volts, 20 volts, 30 volts, 40 volts, 50 volts. And those lines are going to get progressively closer because of the 1/r relationship with the distance. So that's 90% of it. And then just be aware of the fact that if we were to add in a second charge nearby, you need to look at how the contours would lie, as if it was a map with two hills on it instead of one, or possibly even instead of a hill, a sinkhole in the middle somewhere. On a map or on your page where you would draw this, you've only got your pencil, so you'd end up with two lots of black circles, and you would have to label one of them as with positive numbers and one with negative numbers. Here in the picture it's shown as green and blue, but you won't have the luxury of that when you're drawing in your book. This line down the middle genuinely does represent 0 volts all the way to infinity, because if we just have a little look at the 3D plot, you can see that wherever this one is raising the ground up a little bit, the other one's going to be sinking the ground down a little bit. And so all the way along that black line, you have neither gain in height nor loss in height, neither gain nor loss in electric potential. So that black line really is the 0 all the way to infinity.